this video, we're going to explore circular functions. We're going to cover what the unit circle is and why it's important, the different ways in which we can represent angles, the trigonometric ratios sine, cos and tan, and we'll finish up by running through the exact values of the unit circle that you'll be required to memorize for your exam. Let's get to it. The unit circle is a circle with a radius of 1 that is centered at the origin. The circumference of any circle can be given by 2 pi r, and since the unit circle has a radius of 1, we can say that the circumference of the unit circle is just 2 pi. This will be important in a moment, but first, let's talk about the ways in which we can express angles. There are two main ways that we can use to represent angles in math methods. Firstly, we can use degrees. Now, a full revolution of a circle can be completed in 360 degrees. We measure this angle in an anti-clockwise direction from the x-axis. In this example, we can see that the angle is 135 degrees. Secondly, we can use radians. If we express our angle in radians, we're expressing it in terms of the circumference of the circle. We know that the circumference of a unit circle is 2 pi. So one full rotation of the unit circle can be completed in 2 pi radians. Again, this angle is measured in an anti-clockwise direction from the x-axis. We can convert from radians to degrees, or from degrees to radians, using the following equations. For example, if we wanted to convert 135 degrees into radians, we could use this formula and get the result 3 pi on 4. Most of the time in math methods, you'll be given your angle in terms of radians. So if you have a CAS, I would recommend going into your document settings and changing the angle from degrees to radians. You can always change back later, but most of the time, you'll be required to use radians. The functions sine theta, cos theta, and tan theta are all known as trigonometric ratios. They can also be referred to as circular functions. They draw a relationship between the angles within a triangle and the side lengths of that triangle. First, let's understand the terms. The hypotenuse of a triangle is always the side length that is the longest. The adjacent and opposite sides of a triangle depend on where the angle is located. Within a right-angled triangle, the angle that you'll be using will always intersect the hypotenuse and the adjacent side. So if the angle is placed here, then this side becomes the adjacent. But if it's placed over here instead, then this side becomes the adjacent. The side length labelled the opposite side is always opposite from the angle. It's the side length that the angle doesn't intersect with. Now that you understand the terminology, here are the trigonometric ratios. Now, you'll be expected to memorize these for your exam, so let's go through how I do it. I was taught to memorize the acronym SOHCAHTOA. The acronym can be broken down into 3 sections, each with 3 letters. The first letters tell you what ratio is being talked about, sine, cos, or tan. The next 2 letters tell you what side lengths are being used in the equation. In the case of sine, we have opposite over hypotenuse. In the case of cosine, we have adjacent over hypotenuse. And in the case of tan, we have opposite over adjacent. If you know the side lengths of your triangle and you want to find the corresponding angle, then you can use your calculator to calculate the inverse trigonometric ratios arcsine, arccos, and arctan. If you were to draw a straight line from the origin of the unit circle, at some angle theta, it would intercept the circle at a set of coordinates. This line could be considered the hypotenuse of a right-angled triangle. We know that the radius of a unit circle is 1. Therefore, the hypotenuse of this right-angled triangle must also have a length of 1. We can also label the other side lengths of this triangle with respect to the angle theta. What we see is that the x-coordinate of the intercept is given by cos theta, and the y-intercept is given by sine theta. Math methods requires you to memorize the following exact values and their corresponding angles. Yeah, it looks like a lot. In your exam 1, you'll often be asked to solve a circular function, and you won't be able to do it unless you memorize these exact values because they won't appear on your reference sheet. But the good news is, I have a process that makes memorizing this thing much easier than it looks. Let's dive in. This is what a completed unit circle looks like. Now, I know there's a lot there, but let's walk through it step by step. Let's start with the angles that you're expected to know. You're only expected to know the angles 30 degrees and 45 degrees. In radians, these are pi on 6 and pi on 4. That's it. All other angles in the unit circle are just multiples of pi on 6 or pi on 4. Next, we have the exact values that these angles correspond to. You'll need to memorize the following exact values in order: a half, root 2 on 2, and root 3 on 2. The order matters here. Notice how, as we go around the unit circle, that all the coordinates follow this pattern of a half, root 2 on 2, and root 3 on 2 in either the anti-clockwise or clockwise direction. Now that we have our angles and our values, we just need to know where to put them. First, we'll put the angles in. We'll start with increments of pi on 6, and we'll keep going anti-clockwise around the unit circle until we hit 2 pi. Don't forget to simplify the fractions as you go. Next, we'll put in the increments of pi on 4. And just as before, we increment pi on 4 until we hit 2 pi. And suddenly, we've already put in all the angles that we need to know from the unit circle. Now we just need to know the coordinates. Recall that sine theta gave us the y coordinate and cos theta gave us the x coordinate. Here's something worth noticing. Notice that the y coordinates get larger as they approach the y-axis, and they get smaller as they get further away from it. We'll use this fact to order our exact values in correspondence with this. So as we get closer to the y-axis, we're going to start from a half, get up to root 2 on 2, and finally at root 3 on 2. Now we need to talk about the sign of these exact values. The y-coordinates will always be positive if they're above the x-axis, and they'll be negative if they're below the x-axis. So our exact values need to reflect this. We can fill in the x-coordinates using a similar strategy. The x-coordinates get larger as they get closer to the x-axis, and they get smaller as they get further away. We also know that all the x values should be negative when they're on the left-hand side of the y-axis, and positive when they're on the right-hand side. And just like that, we've completed the unit circle. But what about the tan values? You're also expected to memorize those, but here is how you can do so without actually memorizing them. Another way that we can express tan theta is the ratio sine theta on cos theta. So instead of memorizing all the tan theta exact values, you can just use the ones you've already memorized for sine and cos and substitute into that fraction instead. For example, if you wanted to know the exact value of tan theta at theta equals pi on 4, then you would simply find sine pi on 4 and cos pi on 4. Both of those are root 2 on 2, and if you divide any number by itself, you just get 1. So the exact value of tan pi on 4 is 1. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.